Welcome back everyone. We will continue with the representation theory. In the last lecture, we actually defined some basic terminologies in representation theory. So, in this lecture again I will continue with that. First we will actually see what is quotient module and then some isomorphism theorems related with that concept. So, let us start. So, either quotient module or the factor module. So, you must have seen these concepts in other branches of algebra like group theory, ring theory, as well as if you have done some module theory. So, very similar to that, here also one can define quotient modules for modules of Lie algebras. So, we start with Lie algebra, okay, G over C, and then let us say V is actually a module for G. So, V is a module of G. So, other words, there is an action of G on capital V. So, as I said before, this word representation and module can be interchangeably used. Okay. So, we have a module structure on V. So, that is given by this map phi, which is from G to GL of V. Okay. So, let us say given by this. So, now we already seen what is a submodule of V. Okay. So, let us say let us recall that. So, recall a submodule, okay, again it is all G submodules. Okay. So, G submodule W of V is actually a vector subspace. So, it is a vector subspace of V such that when you restrict the action of G on W, then it must be invariant under that action. So, in other words, whenever you take some element x in G and then W in W, so then if you compute the action that x dot W, so which is using that phi, it is nothing but phi x W. Okay. So, this must be inside W for all x in G and W in W. Okay. So, then we call this W is a submodule. So, we like I said, we also use this simplified notation x W to denote this phi x of W or x dot W. So, all these notations are interchangeably used. Okay. So, just for clarification, I will use this in the beginning and later I will use this x W. So, now what is a factor module? So, suppose we have this submodule W. So, then we can actually take this quotient, which is V modulo W. So, this is a quotient space. So, this is clearly a vector space, okay, over complex numbers. So, what it is indeed in terms of elements, so these are all the cosets, okay, which defined using this W. Okay. So, you take all translation of W where x is coming from V. So, that is your quotient space. And basically, so let me recall how you get this quotient space. You define this equivalence relation on V with respect to W. You say x and y are related. Okay. For x y in V, we say x y related with respect to the subspace if and only if x minus y is in W. So, then if you calculate the quotient set or the equivalence class related to this x. So, that will be equal to just x plus W. Okay. So, then if you take this V modulo W, which actually denoted as V modulo W. Okay. So, this with respect to this delta W. So, you take this quotient set which we identify with V modulo W, then there is a natural addition and scalar multiplication integrated from capital V that makes this V modulo W as a vector space over C. So, what is the addition? Let me recall. If given two elements x plus x and y, x plus w and y plus w, then the addition is defined to be x plus y w. Similarly, the scalar multiplication given lambda. So, let us say for x, y and v. So, you have this, and for x in v and lambda in C, we have lambda times x plus w is equal to lambda x plus w. So, this is how the addition is defined and this is how the scalar multiplication is defined. So, now once you have this quotient space, so one can actually try to define this action of G on this quotient space. So, using the data. So, what is the data given? So, given is, so V is already a G module, okay, and W is given to be G submodule. So, now we have this V modulo W, which is the quotient space. We want to make this as a G module. So, how we define? So, define the action of G on this V mod W as follows. Take x in G and then some V in capital V. So, we have x is acting on this V plus W is given to be x V plus W. You compute x V and then take the coset corresponding to that x V. So, this is the definition of the action. So, we have to check this action is first of all well defined, and on top of it, it should satisfy the module's property M1 to M3. Okay, I will check this is actually defines well defined action. So, I will leave it to you to check all the module properties. Okay. So, what is the meaning of whether it is well defined or not? So, we can actually take two different elements V1, V2 in capital V, okay. Say V1, V2, V1, V2 in capital V such that V1 plus W is same as V2 plus W. So, what is the meaning of that? So, this is if and only if using our definition, if you go back. So, V1 and V2 are related using this relation if and only if this difference should be in W, okay, because the coset is nothing but x plus W. So, this says this V1 minus V2 should be element of W. So, now you can see that because W is a submodule, if you act with x on this V1 minus V2, this is again element of W, as W is a G submodule. So, this implies x dot V1 minus x dot V2 is in W. So, then it is easy to see that x dot V1 plus W is nothing but equal to x V dot plus W. Okay. So, this proves whenever you have two cosets equal V1 plus W equal to V2 plus W, then the corresponding images x dot V1 and x dot V2 they are same, okay, the difference is in W. So, this actually defines well defined action on V mod W2, V mod W where you take x comma v plus w, then you send it to x v plus w. Okay. So, this is the phi bar which is actually defined using the phi. So, I will leave it to you to check this phi bar actually gives module structure on V mod W. Okay. Check phi bar gives module structure on V mod. Okay. So, this is not that hard, one can easily check. So, now with this we actually have our factor module or the quotient module. So, now you can actually easily prove the expected isomorphism theorems. Okay. So, let me actually see some examples. Okay. Let me show some examples before moving to the isomorphism theorem. So, we already have this adjoint representation, okay, given this G Lie algebra. So, we have this add map from G to GL of G. So, this is going to give us module structure on G. G is acting on G via this adjoint map. So, that is the adjoint representation or adjoint module. So, now if you think about it, so what will be the sub representations or sub modules? So, ideals will be actually sub representations for this representation. Okay. If I is a sub module of G, okay. So, I am thinking it as odd representation if and only if I is ideal inside G. So, now if I is ideal, if I is an ideal inside G, so then we can talk about this G modulo I. So, which is actually a Lie algebra. Okay. So, this is also a Lie algebra, but one can also define what is called this G action on this G modulo I and make it as G module. Okay. So, that is what we have seen. So, here we can take this quotient and then we can make into a module for G. So, what is the action? So, if you think about it, the action is given by x dot y plus I. So, which is the coset, then it is just given by, again we are using the adjoint action. So, this has to be x y plus I. Okay. So, this is action that makes, okay. So, G acts on G mod I, so via star. Okay. So, this is indeed G module action on G mod I. Okay. So, that is easy to see. So, you can actually think about it. So, I will leave it to you to check. So, there is another action of G mod I on G mod I, okay, because G mod I is a Lie algebra. Okay. So, this is something you check. So, G mod I also acts on G mod I, because this is a Lie algebra and you can think this as a vector space. Okay. So, again how it acts? Via adjoint action. So, now you have like different action on G mod I using like two different Lie algebras. One is using G, another one is G mod I. But if you think about it, they are closely related because both are given by this star only. Okay. Okay. So, let us move on. So, there is a trivial representation for any Lie algebra. Okay. If you start with G, so which is a Lie algebra, and then let us say V is just a vector space over complex numbers. So, then we can make G to act on V trivially. Okay. We can make G to act on V trivially. So, what I mean by that, you can define this trivial representation as follows. So, G to GL of V given by phi of x equal to 0 for all x in G. So, it is easy to see that this map is definitely a Lie algebra homomorphism. So, that means if you take x and then V, where x in G and then V in capital V. So, you are declaring x dot V is 0 for all V in V and x in G. Okay. So, this is called trivial representation. Sometimes we also say, so we call actually, let's fix some terminologies. So, we say this is actually a trivial action. Okay. Let us say, let us call it trivial action on V. Okay. We say something is a trivial representation if dimension of V is one dimensional. Okay. If dimension of V is one dimensional and G acts trivially, then we say V is a trivial representation. So, we should not actually get confused with trivial action and trivial representation. So, trivial representation, whenever I say something is trivial representation, then I mean the dimension of the representation is one dimensional. Okay. So, we also actually denote this by 1 C or just by C. Okay. All this notation can be used. So, I will explain later why I want to use this 1 C. Okay. So, that will become very clear if we start talking about tensor product. But anyway, you can also use this C to denote this trivial representation. So, we already seen that SL2C naturally acts on this C2, okay, because SL2C is sitting inside GL2C. So, using that 2 by 2 matrices, so using the natural action of 2 by 2 matrices on C2. So, we get action of this SL2C on C2. So, I will actually leave it to you to check. So, this is indeed irreducible representation. Okay. So, this is actually an irreducible 2 dimensional representation of SL2C. Okay. So, it is not hard to check the adjoint action of SL2C is also irreducible, because as we saw earlier, the only sub representations are ideals of SL2C, because SL2C is simple Lie algebra. So, that actually tells us that adjoint representation of SL2C is also irreducible. Okay. So, this is a fact, adjoint representation of SL2C gives us 3 dimensional irreducible representation of SL2C. So, later in the next class I will classify all finite dimensional irreducible representation of SL2C. So, of course, those include all these 3 examples. So, one is one dimensional trivial representation, another one is 2 dimensional this natural representation acting on C2, third is this adjoint representation acting on SL2C via adjoint map. So, here is a simple exercise. Suppose dimension of V is one dimensional. Okay. So, let us say dimension is 1, where V is a representation of SL to C. Okay. So, then I want to claim that the action of SL to C on this capital V must be trivial. Okay. So, we claim that. So, let us say this is given. So, you have a one dimensional representation of SL to C. So, we do not know anything about the action of SL to C, but we want to claim that the action of SL to C on this V must be trivial. So, how one checks this? So, one can use this fact that SL to C, the derived algebra of SL to C is itself. Okay. So, because the derived algebra of SL to C is itself, so it is enough to prove for basis elements. Okay. For example, if you take, so what is the basis? Recall. So, you have x and then h and then y. So, where x is given to be this upper triangular matrix, h is given to be the diagonal matrix, and y is given to be the lower triangular matrix. So, then we also have this very explicit commutator relations. So, x y is h and then h x is 2 x and then h y is minus 2 y. So, from this it is easy to see each element in the basis is actually a commutator of 2 element. Okay. So, that means actually if you take the action, for example, let us take the x action. So, x is nothing but h by 2 x. So, this is acting on this capital V. So, this is one dimensional. So, how this h by 2 will act? Okay, h by 2 will act as some scalar. Okay, let us say V is spanned by this small vector V. So, V is non-zero. So, then this h will act on V as some lambda x V, and then this y will act on V as some lambda y V, and then this h will act as some lambda h V. Okay. So, in particularly if you compute x v, there is another way to compute x v, because x is given by the bracket h by 2 comma x. So, that is also acting on V. So, if you write it very explicitly, this is h by 2 x minus x into h by 2 acting on V. So, then you can see that on the one side you get lambda x v, on the other side you are getting lambda x lambda h by 2 v minus lambda h by 2 lambda x v. So, if you just because lambda x and lambda h by 2 both are complex numbers, you can see that if you take it out. So, these two things actually gets cancelled, you get 0. So, this proves that lambda x must be 0. Okay. So, indeed if you are writing this x as commutator of two things. Okay. So, then for example, like each element acts as scalar. So, the commutator, because both of them, this h by 2 and x, both of them leave this one dimensional space invariant. If you take trace of this commutator, that will be 0. So, that is all we are using. So, then that makes the trace of x to be 0, but the trace of x will be lambda x times 1. So, that forces that lambda x is 0. So, similarly, you can use the same idea to prove lambda y 0 and as well as lambda h by 2 or lambda h is 0. Okay. So, that proves that SL to C acts trivially on any one dimensional representation. So, that makes it actually, if you start with any one dimensional representation of SL2C, then it must be isomorphic to this trivial representation that we already see. So, so let us move on. So, to state this isomorphism theorems, we need to actually define what is called homomorphism in the category of representations of G. So, we will actually fix the Lie algebra, okay, G, and then we want to consider all the representations of G. Okay, those are all the objects in our category. So, now, so what will be the homomorphism in this category? So, it is natural to define, if you have seen what is homomorphism in the like G representations for G is group. So, it's the same way one can define it here also. So, basically given two representations V and W, so let us say G modules. So, a homomorphism theta is a map from V to W. So, it must be C linear map to begin with, such that, so this should commute with the action of G. So, what is the meaning of that? If you take theta of x v, so that should be equal to x times theta of W, and sorry, x times theta of v. And this is true for all x in G and v in V. Okay. So, this should be true for all. So, in particularly, so what does it mean? So, it means, so you have this map V to W theta, and then you have this action given by the element x. Okay. I am suppressing the notation, basically let us say this is given by phi. So, let us write it very explicitly. So, let us say phi is the representation that is defined on capital V, and then let us say phi 1, and then phi 2 is the representation defined on capital W. So, then what is this x that we are talking about? This is phi 1 of x. So, which is a map from V to V. So, now you have this theta which is defined from V to W. So, now you have another map from W to W, that is again given by phi 2 of x. So, now the equation, this star means this diagram must commute. Okay. So, if I take some V from here, and then this is mapped to theta of V on the right side. Okay. There is a way to actually reach using the action. Okay. So, you can go to this x dot V, which is phi 1 of x applied on V, and then you can go to again using the theta applied on phi 1 of x of V. So, now you can also go from V to theta of V and then come back to using this phi 2 of x, okay, phi 2 of x applied on theta of V. So, these two should be equal. Okay. So, you start with V, come to phi 1 of V and then apply theta on that. That should be same as you apply theta first and then apply phi 2 of x. So, these two must be equal. So, that is the meaning of this diagram commutes. Okay. If theta satisfies this property for each and every x, okay, this diagram commutes for each x in G, then you call this theta is actually G module homomorphism from V to W. Okay. So, now it is not hard to check, here is a proportion. If theta is actually a G module map or G module homomorphism, then the kernel of theta and image of theta. So, they are submodules in respective modules. Okay. So, this is submodule of V and this is submodule of W. So, these are all G submodules. Okay. So, let us check for the kernel. So, what is the proof? So, what is the kernel of theta? The kernel of theta is those V in capital V such that theta of V is 0. So, we need to prove that if I start with x in G and V in kernel theta, then if you apply x dot V, that is also should be in kernel theta. So, this is what we need to check. So, let us see how this x dot V is actually we one can get. So, you apply theta of x dot V. So, that is what you need to check. We need to get this is 0. But what is theta of x dot V? Theta of x dot V, if you go back to the definition, it says theta of x dot V is x dot theta of V. Okay. Maybe I will put this dot so that we are talking about action. So, that means theta of x dot V is same as x dot theta of V, but theta of V is 0. So, x acting on 0 will be 0. So, that will prove that theta of x dot V is 0, that says x dot V is in the kernel theta, and this is true for all x in G and V in kernel theta. So, we get kernel theta is submodule for V. So, G submodule. Similarly, one can check for image of theta. So, image of theta is nothing but theta of V, where V is coming from capital V. So, it is easy to see that this is actually a subspace of W. Okay. So, now if you start with x in G and then some W in image of theta. So, we want to prove that x dot W is in. So, we want to prove that x dot W is in image of theta, but W is in image of theta. So, that implies W will be theta of some V for some V in capital V. So, now if you compute x dot W, so that will be x dot theta of V. So, which will be theta of x dot V. So, which is same as theta of, sorry, we wanted to prove x dot W is in the image. Okay, this is x dot V. So, this you can see that this is already in the image. So, x dot W is nothing but theta of x dot V. So, that is again in the image of theta. So, this proves that image of theta is again submodule for the image space or the codomain. Okay. So, now we are ready to actually state the isomorphism theorems. Okay. So, actually more or less only thing that we need to check in this isomorphism theorems, whether the maps that we have defined are all well defined maps and whether they are G module maps. So, I will leave it to check all of this, okay, because from linear algebra course we know that such maps are there. So, using those maps one can actually establish the required isomorphism. So, let me just state this result. So, here is the isomorphism theorem. So, as before the very first statement is about having a having a G module map and then relating the quotient module V modulo kernel theta and the image of the theta. So, start with G being Lie algebra over C and V and W be G modules, and let us say theta is G module homomorphism. So, then we can actually, we already seen that kernel theta is a G submodule of V and then image theta is G submodule of W. So, we can talk about V modulo kernel theta. Okay. So, there is this induced map from theta tilde from V modulo kernel theta to image of theta given by, so V plus kernel theta is sent to theta of V plus theta of V. So, this is an isomorphism. So, that we know this is a linear isomorphism, but the claim is, so this is indeed G module isomorphism. So, G module isomorphism in, it is G module homomorphism which is again bijective. Okay. So, bijective is already there. So, only thing need to be checked, because there are two modules are given. Okay. This is the factor module V modulo kernel theta, on the right side we have this image theta. So, this theta tilde which we have defined, we need to check it is a G module map. So, that is more or less trivial to check, because theta tilde of x dot V kernel theta. So, this is going to be equal to theta tilde x v plus kernel theta using the definition of factor module. So, then this is same as theta of x v. Okay. So, then if you think about it, theta is actually G module map. So, x is coming out. So, then you get x times x acting on theta of v, then you get x dot v plus theta of theta tilde of v plus kernel theta. So, this is what we wanted. So, theta tilde x dot small v plus kernel theta should be equal to x dot theta tilde v plus kernel theta. So, this is something very easy to check. So, it's an elementary fact from linear algebra. So, this theta tilde is an isomorphism. So, that I am not going to check, I will leave it to you to check. So, what is the second statement? If u and w, they are actually submodules of V, again G submodules. So, then we can talk about these various spaces. So, u plus w, it is easy to check, u plus w is again G submodule. So, that I will leave it to you to check, and then w will become automatically G submodule of u plus w. So, we can talk about the quotient u plus w modulo w. So, this will be naturally isomorphic to u modulo u intersection w. Okay. So, this is something I will leave it to you to check. So, here lots of many facts are there. First of all, u plus w is a G submodule of V, and u intersection w is also G submodule of u as well as V, and w becomes G submodule of u plus w and we can consider these two factors and they are isomorphic. So, here is the third statement. So, suppose u is contained in w, both of them are submodules of V. So, then we can talk about this w modulo u, that is inside V modulo u. Okay. So, this becomes G submodule, and we can talk about now quotient of these two, V modulo u quotient by W modulo u. So, then this will be isomorphic to naturally V modulo u. Okay. Again, once you have actually defined the natural isomorphism, then we need to check that natural isomorphism is actually G module isomorphism. Okay. So, that is actually something one can easily check. So, I will leave it to you to check. Okay. So, with this we have this fundamental theorem of isomorphism for modules. So, I will stop here. I will continue with Schur's lemma and some consequences of Schur's lemma in the next class. Thank you.